Okay, so this is another Python tutorial. In this one, we're going to talk about analyzing data from ECCO, which you may have heard of. This is V4, so version 4. You may have heard of this from some of the other instructors. So Dimitri Menemenlis has been very involved with ECCO. He's one of the ones that makes this all happen. He's currently in person, but last year he had a recorded tutorial, recorded lecture about ECCO, which I'm happy to share if there's interest. It's on the YouTube channel. And if you were around earlier today for the virtual session by Jinbo Wang, he also talked about how to access ECCO data through the NASA servers. So you'll learn here, there are a few different ways that you can access some of this data. This ECCO data is currently available just straight on our Jupyter Hub at the moment. So we don't have to go onto the NASA server. So we can just access it directly. So before I get too much into this, just wanted to go over briefly what ECCO is, in case you have missed some of those previous lectures. So ECCO stands for Estimating the Circulation and Climate of the Ocean, which is a bit of a mouthful. Just gonna make this window a bit bigger. And they call it a state estimate. So they call it the Ocean and Sea Ice State Estimate. This is slightly different from an ocean model, although it's very similar. And in fact, it's essentially it's a reanalysis data set. So if you're familiar with reanalysis data sets, what they do is combine a kind of free-flowing model with observations. So in this case, what ECCO does is it combines the observations from both in situ observations and satellite remote sensing, and they work it into the model. So you get kind of the best of both worlds. And what ECCO does that's a little bit different, this is said here, it's a little different in relation to other ocean reanalyses, is that most of these reanalyses will have the model going and then they use data to fit the model as it goes into the future. What ECCO does is it actually uses all of those observations and integrates them into the model at all time. So it has this nice sentence here: only ECCO state estimates provide an explanation for the underlying physical causes and mechanisms responsible for bringing them into existence. So you can really, it's really kind of fitting the model to the data. It is currently 1 degree horizontal grid cells. And the time period is from 1992 to 2015, although I actually think this is out of date. I think it is now up to 2017. I think I'll drop this in the chat if anyone wants to check out this website. This also has a tutorial about how to use ECCO data, some of which I will be showing you today. So I wanted to show this. This is on the ECCO homepage. And this plot here is the sea surface height linear trend from 93 to 2017. So you can see that it does go up to 2017 now. And negative here means that sea surface temperature, or sorry, sea surface height is going down. Positive is that it's increasing. And what we have here is this really nice graphic on the website, where if I pull this all the way over, we just see observations. So these are observations that are being integrated into ECCO. So both from in situ and remote sensing. And if I drag this over, we can see that over on the right is the ECCO model output. So you can see that it's smoothing out these fields. But as you go, you can see how well the model matches these observations. And it's pretty tricky business to actually make this work. So this is quite a nice product that NASA has made for us. Is there a question? Hello. Okay. I'm muting you if you want to speak, please unmute and ask me a question. That's totally fine. And down here is just another example. In black are some observations of sea level anomaly. So again, how this is basically showing how sea level is increasing, which we all probably know. And ECCO is in red, so we can see just how well it matches the observations. So anyway, ECCO is a pretty great product to have, and it's really nice that it's really at our fingertips on this Jupyter Hub. So I'll dive into doing some data analysis. Some of this will look very familiar to what we did yesterday, where we're doing multi-dimensional data analysis. And this is, again, in multiple dimensions. You have X and Y in the horizontal, and then time is a third dimension. And this one also has vertical levels as well. So it actually has 4 dimensions. Okay, so I will get started. So if you've been at the other Python sessions, you know that we start by importing the packages that we need. So just a quick recap, we're going to import Xarray. Xarray, I have a link here. Xarray is what I talked about in the multi-dimensional lab yesterday. So you can check that out for more details on Xarray. And Xarray is, if you're familiar with pandas, is basically the pandas equivalent for multi-dimensional data analysis. So this is the package you want to use if you have multi-dimensional data. We're importing NumPy. It's kind of a base package that we use for a lot of things. And we're importing matplotlib, which is a plotting package. Okay, so we're going to load the data. And if you were at yesterday's session, you know that when I say load the data, I don't actually mean that we are actually going to load the data in. Instead, we're just going to load in the metadata because this is such a big data set. And this data is currently stored on the cloud as a ZAR file. So we can click here and go to, this is the website for ZAR. And it says here, ZAR is a format for the storage of chunked, compressed, n-dimensional arrays. So ZAR is really friendly on the cloud, and it works really well for multi-dimensional data sets where they need to be in chunks to be able to work with them. And by chunks, we basically mean just chopping them into smaller pieces that we can actually do computation on, since it's hard to do computation on one giant data set all at once. So here's some more links here. There's a tutorial if you want to know more about ZAR and a few other things related. So we are going to load the data just as we did yesterday. You'll notice it's a different, it's still in the Pangeo catalog, this Pangeo data store, but we're loading in a different data set this time called ECCO. So I will evaluate that cell. And by typing DS at the end of the cell, it will print out what DS is. And so DS I've defined to be this data set. And so here is what we get. So these are all of the dimensions in the data set. These might look a little different than what we've seen before, but we still have time. I believe this is monthly data, which is why this time dimension is much smaller than some of the previous data sets we've looked at, which had daily. We have these several different, we have K_L, we have K and a few other Ks. K is the vertical index. So I is the X index, J is the Y index, and you can see that we have a few others. We have I, G, and JG. So I will get into this a bit later, but the reason why we have these different indices is because ocean models tend to have grids that are offset. And we'll get to this at the end, hopefully. But we have something like this, where we have T would be for temperature, for instance, and U would be for horizontal zonal velocity. And we can see that these are actually at different points on the grid. So it's getting a little bit kind of nitpicky about how climate models run. I encourage you to look at some of the content from last year's School by Joseph Ansong and others, and they will talk a bit about these staggered grids, as we call them. And there's a reason for doing this. It says here it's favorable for conservation properties and can make doing derivatives much simpler. So anyway, that's why we see a few different things there. We also have this dimension here called face. This is very specific to ECCO. And I have to admit, I don't use ECCO much, so I've basically only presented this at last year's and this year's school. But face is they've basically divided up the data set into different faces or tiles. So we'll see those in a bit. We have a list of coordinates here. So we can see all of these. I'll note depth because we're going to use that one in a moment. That's the ocean depth. And that depends on the face and then the J and I indexes. And we can see what that looks like. So that's the coordinates. We've got all of the data variables, and there are a lot of them here. And again, we can just click this file logo over here, and you can see what they are. So this one is vertical advective flux of salinity. And you can see what it looks like. So here we have these two different representations. That's because it's actually a 5-dimensional array. And so here, instead, there's no way to depict a 5-dimensional object on a 2D screen. So they've just made it saying, well, 2 dimensions look like this and the other 3 look like this. Okay. Are there any questions at this point? Okay. Great. So if there are no questions, I will continue on, but again, interrupt at any time. So I'll keep reiterating this. Note that the data has not been downloaded yet. All we've downloaded, all we've imported is this metadata. So none of this is actually data. It's just telling us about the data. So it's just saying, here's a list of coordinates. Here is what those dimensions are. And here is the name of these dimensions. So it's a lot of useful information. And in fact, it's most of the useful information I need to start doing some computation. I don't really need to see each of the individual, temperature points to really know what I want to do with this data set. So I mentioned this yesterday. This is an example of lazy evaluation. So it doesn't actually evaluate anything until you are ready and you say, I want it evaluated. So we just do everything in terms of metadata for now. And again, so some of this is repetition. I think it's good to have some repetition. Each of these variables, if I click this open again, if you see here, it says Dask array. So they're all stored as chunked. You can see chunk size here. Chunked Dask arrays, which helps us with parallel and distributed computing. So I was curious to know how big the data set was. So the way we can do that, we define the data set as DS. So I can say DS, and then I can call n bytes. So that means number of bytes. And then I just divide that by 10 to the 9th power, which gives me the result in gigabytes, which is just a little easier to read. And if I run that, it says 152.8. So it's about 153 gigabytes. That's pretty big. That's certainly too large to be able to operate directly on your local computer or even here on the cloud. It's significantly smaller than the one we looked at yesterday, but still large. So now we're going to look at, we're going to do a bit of plotting. We're going to plot the ocean depth, and depth was one of the coordinates. So here we're just defining coordinates, which is ds.coords, that accesses the coordinates. I'm just going to make that a data set. Again, this is a little bit of a trick to make things work faster. And reset coords means that I'm deleting the other coordinates that are not needed. So this is a bit of a hack to just make things work a little faster. But I'm just defining my coordinates here. And here you can see the list of coordinates is much smaller than the coordinates up here where there were 37. So now we have this new data set. See, it's defined here as an X-array data set. And let's move forward. So let's make a plot of depth. we want to know ocean depth. So depth is a 2D field, but as it shows here, it looks like it's a 3D array. It's stored as a 3D array. And so we have J and I, which are the Y and X indices, but it also has this face dimension. So we're gonna have to figure out what to do with that. So let's print out chords.depth and let's see what it looks like. So here we go. And here we can see that face, we have 13 faces. If I try to plot this right away, X-array has this, can interpret this. So I was showing yesterday, to plot something in X-array is often really quick. You can just say dot plot. And if it's a one-dimensional plot or a two-dimensional plot, it will just interpret that and give you the plot you want. If I say dot plot right now on a three-dimensional data set, it ends up giving me this histogram because it didn't know what else to do. So here it's saying, well, depth is on the x-axis. I don't even know which one. I or J is on the y-axis. And then the actual values here is the other one. This isn't very useful to us. What we want to see is a map. So I am going to use this feature of X-ray plotting, which is very helpful. I actually didn't know about this for a couple of years when I was using X-ray plotting, where I actually want it to plot. So we know that there are 13 faces, and these are basically tiles of the actual data set. So I want to plot each of these tiles. Sorry, I'm just going to mute. I was hearing a little bit of noise. So I want to plot all of those faces. So here I can use this COL equals, which is basically for column equals. And then I can plot all of the faces as different columns, which looks like a subplot. This here is saying that I want only 5 columns before you start wrapping and put more columns. So once I do this, we'll see what it looks like. So here we go. So this is what ECCO means by faces. So it's got face 0, face 1, and so on, all the way up to face 12, which is 13 total. And you can kind of start to make out some land masses. You know, this one down here kind of looks like South America, but this doesn't look very helpful. It's nice, it looks pretty, but we don't actually know what's being plotted here. This is where we have to use a bit of help. So I copied and pasted this function that was written by some of the ECCO folks. And it is basically telling Python how to plot this so that it'll look nice. So right now you're going to have to kind of take this as given. But if you have been following along with all the Python sessions, you might still look at it and say, oh my gosh, this looks like gibberish. But if you start to look at it line by line, you might still understand a little bit about what's going on. So we're loading packages that we want. Notice that we load Cartopy, which is the map plotting tool. So we're going to be using that today, but just within this function. So this is starting a class. That's kind of a very Python specific thing. This def call is actually defining a function, and these are the inputs to the function. Here you might remember we're accessing, so DS was our data set. We're accessing something within that, XC. Yesterday I mentioned if you say dot values, you get back the actual values of the array as opposed to just the metadata. And you might not know what revel means, but this is one where you can Google and you can say, what does Python revel mean? And this means, in this case, it's flattening the array. So if you have a 2D array, it's going to make it into 1D. And they do that because it makes sense later on. So I'm not going to go into each line here, but if you really start breaking it apart, you can start to understand. And again, maybe you don't know what this function means. You can Google that. But once you start getting a hang of the syntax that, you know, these parentheses mean that it's a function, and so on and so forth. So then down here, we can see that it's calling pcolor mesh. That's a plotting tool. So that's where the plotting takes place. So anyway, I'm just going to run that, and we're going to take that as a given for now. I will note that this function is actually, I'm going to be uploading, I forgot to upload it before. There'll be another notebook from last year that I will add. If you go here into the hub, you can see labs from 2021. I'm going to include another ECCO lab here from last year, and that one uses a package called ECCO v4py. You'll see that, and that package includes this function in it, which makes things a little bit easier. So anyway, I've run this, we're going to take that as given. And now we notice that this, let's see, LLC mapper is what we're calling here. So if we go up here, we see that this class is called LLC mapper. So what we're doing is calling this whole kind of all of these functions that just occurred, and we're giving it the coordinates. So now I can just call mapper and put coordinates.depth, and it should give me a plot. Nope. Oh, NP is not defined. That is interesting. That happened to me earlier. And it's because I didn't evaluate this cell. So this happened to me last year, I think. So I'm just going to take this time as an example. Here I got an error. Sometimes you might see an error and say, oh no, I did something wrong. Error messages are actually very helpful, usually. Sometimes they're not. This one was very helpful. It said, name NP is not defined. So I know that NumPy is usually called NP. So like right here, for instance, we have np.meshgrid. So what this is telling me is that I didn't import NumPy. Then I go back to the top and say, that's funny, I wrote it down. And I did, but if we zoom in, you can see that these brackets on the left are empty. That means that I haven't run the cell yet. So that was just my bad. I forgot to run it. So now if I shift return, you can see a number here. It means it's the 9th cell to have been evaluated. Now that's been evaluated, I should be able to go back and get this without any errors. So that's kind of what I encourage you to do. If you have an error message, right at the bottom, it should say what the actual error was. Sometimes it's a really long error message. Sometimes you want all that. Sometimes you just need the bottom line to know what you've done. And if you don't know what the error message means, you can Google it. I do that a lot. I'm like, oh, I don't know what I did. And I Google that. I'm actually going to give a session tomorrow on how and where to ask for help when doing Python programming. And I might include a little bit about these kind of error messages if you want to join them. Anyway, look at this beautiful plot that we made. So this is very nice. It has this nice projection. It has a color bar off to the side. It has the continents colored in gray. Looks really nice. So this looks much more understandable than this, which is very hard to actually tell what's going on. So if you've been at all the Python sessions, you might start to see that working with each data set is very different. So each data is stored very differently and is organized very differently, which means we need tools. A lot of tools can be used kind of across data sets. So I'm using Xarray here, but I needed a little bit more help. I needed this function here to help me actually interpret the data. And so now you have it and you can use that. Okay. So now we're going to select some data. So let's look at temperature, which is given by this theta variable. And as we saw yesterday, if you don't know, if we're saying, let's look at temperature, and you're like, I don't know what variable name that is, you can go back up here to data variables. You can kind of look around. I usually look for something like temperature or SST. In this case, it's theta, which is a little bit more cryptic. But I can look here, and I can click and say, right, theta is potential temperature in degrees Celsius. Great, that's what I want. So that's how I know I want theta below. And we are going to use the .cell.sel method, which selects a specific time. So yesterday we saw the iCell and cell. iCell is based on index, cell is based on the actual value. So here we're saying instead of saying I want the 5th time step, we are saying I want this very specific time, and you give that here. And then we also, k equals 0 is for the surface. So we're just going to look at the surface layer. And we're going to call this SST. So again, this is all the metadata. No actual calculation has been done, but this is saying SST is of this size. And now if we plot it, that will actually cause the data to be loaded. And that's where we're actually going to do some computation. So again, we're using our mapper function to plot SST. This is passing in the color map, which is this red-blue. And here we go. This looks very nice. So this is the sea surface temperature with this really nice color map and these nice grayed out continents. Are there any questions up to this point?
So I have, can you hear me?
Yes, yes, please go ahead.
Calling up this data, this sea surface temperature data, you were highlighting some data set there when you went to highlight SST, and you came up with this up here, there, yes, this. So what were you doing to run this data? How did you run the data directly? To give us that figure below. Okay,
so if I understood you correctly, you kind of want to understand how I came up with this line. Is that correct?
Yeah. Yes.
So if we go back to where the data, let's see. So here, when I said we load the data, and again, load is actually a lazy load, but we called the data set DS for data set. That's pretty common. And we loaded it in here. And I have these nice drop-down menus of the dimensions. That doesn't actually do anything. Coordinates. So coordinates are, so the dimensions are kind of indexes. The coordinates actually have some more physical information. For instance, the actual depth. So K is a coordinate here, and it is the Z-grid index, but it doesn't have any physical meaning. It just is 0, 1, 2, 3, 4, and so on. Whereas depth actually has information about the actual physical depth. So that's what coordinates are. So variables are usually what you kind of want to plot. Those are the things that you work with, like temperature, humidity, precipitation, all of those things. And so there's a list of all of the variables here. So to access any variable, I'm going to type ds and then dot the variable. And that means I'm going to basically grab that variable only from the data set. So that's what I did below. I knew that theta is temperature. Again, that takes a little bit of getting used to the terminology. Theta is typically the Greek letter that is used for potential temperature in ocean models. And so here they named it theta instead of temperature, which would have been a little nicer, but that's okay. And so I said, okay, the variable name is theta in all capitals. So if we go back down here, where was this? So I'm saying ds dot theta, and we can just do that here. If I just do ds dot theta and print that, it says, okay, you've grabbed this data array called theta. And then here I'm just selecting a time and a vertical level. So here you can choose whatever you want. This was 2000. This is January 15th, 2000. You can choose any time. If you don't know what times are available, you can do ds.time. And this prints out some of the time stamps for you. So this, you can see that it starts on January 15th, 1992. And then you can see the next one is February 13th, and then March 15th, and so on. There's this ... here. So that has all of the rest of the time. And you can see that it ends at 2015. Yeah. And so here I could put, any of these in this format. This also tells us that it's monthly data, January 15th, February 13th. So we could put in anything here. We could put in 2015. Let's put June 15th. Let's see if that works. Nope. Okay, so it probably doesn't have that far out, or it's maybe June 14th. Let's see. Okay, so that was just, some of these are 14th, some of these are 15th, I think, depending on whether the month has 30 days or 31 days. So again, there's can be a little bit of back and forth. You saw I had an error and just said, whoops, I probably did it wrong. But that's how I got that line. And now we can make the new plot for 2015. And hard to tell the difference. Looks similar. Did that answer the question?
Yes, please.
Okay, great. Thanks for that question. Okay, so, and I know a lot of this, it seems like, I'm saying, okay, let's plot this, let's plot that. Normally, if you're actually doing your own analysis, you'd look at the data and say, okay, what do I want to look at? What would be interesting? And here I'm just saying, let's plot this and let's plot that. But yeah, normally this is maybe a little bit of a back and forth where I might say, okay, I want to look at this 2015 and then say, well, actually, that doesn't, I don't know if that's as interesting as the one from 2000. I'll go back to the one from 2000 and plot that. There's a lot of back and forth that I will do in these notebooks. And one thing I really like about notebooks like this is that they are more interactive. So here I've printed out, have all this output. I can actually just close that so we don't, and just has three dots, so I don't have to look at all of that output. But I can just look at the figure while in line with the code, which is very nice. So before Jupyter, we mostly were running Python scripts where you'd kind of run everything and something would pop up in a new window if you were plotting. But here we can see the code that led to the figure, which is really handy. So I really like these Jupyter notebooks. Okay, how are we doing on time? Okay. Did someone have a question? Okay, don't hear anything. All right, let's do some calculations. So now we're going to take that same theta variable. So we're going to keep working with temperature. We're again going to select k equals 0. So this means surface, just to make things easier so we don't have a three-dimensional data set. But now we're going to take the time mean. So I can do that very easily. We saw this yesterday by saying dot mean and then writing dim, so the dimension equals time. And if I run that, it runs really quickly. And we can see now that time is no longer a dimension because we've averaged over it. So we're left with this three-dimensional object. But notice we haven't actually done any calculation. So what we are going to do to actually calculate is call dot load. So mean SST at the moment is just metadata saying this is what we will do once you tell us to. Once we decide, yes, we want you to actually compute that mean, then we can say mean SST.load. What this does is it loads the actual data. So it actually does the number crunching. It takes the time mean of the sea surface temperature. And then it saves the output into this mean SST variable. And this percent time, we saw something similar yesterday. This percent time times how long it's going to take. I'm actually going to start running it because it takes a little while. This will time, it'll spit out a time of how long it took to load this data. So yesterday we saw percent time. That's basically the same thing, but if you have multiple lines. So percent time just tells you how long it takes to run a single line. If you put percent time at the top of your cell with multiple lines, it'll give you the time it took for the whole cell rather than just that line. So you can see this star here. This means that it's loading, like it's going. Okay, and it just finished. And we can see here, wall time was 33.9 seconds. So, it's not too bad. It was reasonably quick. And we just loaded that into our notebook. So now that we have mean SST loaded, we can plot that. So now instead of plotting a single point in time like we did before for 2000 or 2015, now we're plotting the average over all of those years. So this is the average sea surface temperature for all of the ECCO data that we have available. And it is a little hard to tell a difference. But here we can see, let's see, can we see a bit more? This one looks a little bit smoother, which usually happens when you average. Okay, so that was all great. It worked pretty quickly. 30 seconds isn't too bad. But we can speed things up by using Dask. So Dask, I mentioned yesterday and gave a brief overview. Dask is a package that we can use to run our code in parallel or in a distributed way. So sometimes we have calculations that are done on each point, but they're all independent. And instead of waiting for each calculation to be run in series, we can run them at the same time and it will run much faster. If it's a small thing like this, it doesn't make a big difference, but this is good. It's a good illustration of how we can use Dask to help speed up our computation. So in this case, as we said here, the main bottleneck for this type of data analysis is the speed at which we can open the data, read the data. And that's because the data is so large, it's stored in multiple different files. It's actually on the cloud, we call it object storage. So it's actually not files, but they're a bunch of different objects, basically like files. And opening and closing each of them takes a long time. So we can use Dask to help speed that process up because we can open them in parallel. So we are going to import these two libraries. So we're going to say from Dask gateway, import gateway cluster. These are things that you'll just have to copy and paste. So Dask gateway is a specific way of running Dask that runs on the cloud. So that's why it's called Dask gateway. And we're using Dask distributed. That's the distributed computing or parallel computing portion of Dask. So here we're setting up our cluster. So what we're basically doing is grabbing, we only have so much kind of memory and computational power within our home notebook here. What we're doing is we're going to set up a cluster. A weird echo. Mute. Sorry about that. Okay. So we are going to kind of set up some CPUs, basically. Basically a little cluster that we can do some computation on. We're just going to set that up in this cell. And we can make it as big as we want. We can scale it up. We can scale it down. That's what's really nice about using cloud computing, is we can kind of run clusters on demand. So that's what we're doing here, is we're demanding a cluster. So here I'm initiating and saying, I want my cluster to be a gateway cluster. I'm going to scale it up to 5 workers. So this is basically saying how much computing power do we want? And there are 2 different ways to do that. This is saying the number, we want the number of workers. There's a lot of vocabulary here. Number of workers to be 5. You can also specify the amount of memory. So in this case, we don't necessarily need a lot of memory, but what we want is several workers that can open the files in parallel. So we're just going to scale it to 5 for now. This is a bit of an art of knowing how much to scale things. Then I define the client, which we'll see in a moment. And I'm going to print that out. So I'm going to actually run this. I should have run that before because it takes it can often take a couple minutes for this to start. So this is essentially asking for computational power on demand. And it works pretty well, but it can sometimes take a couple minutes, which is still pretty good. So we see that it just printed something out, but it lists at the moment that we have 0 workers, we have 0 threads, and we have 0 memory. So that means that the cluster has been initiated, but it hasn't actually spun up yet. So we don't have the computing power ready yet. So this is why I print out, by typing out cluster here, it prints all of this out. And now we can wait. We're just going to wait here until these numbers appear. So you can see that this is actually a link to the dashboard. I'm going to click this. This is a link to the Dask dashboard. So it's empty right now. Once it spins up, we'll see a little bit of action. And then we're going to watch this while I do a computation, and it will actually show our computation being run. So we're still going to wait. I'm just going to comment that there's a lot of advanced computing in this notebook. So if you're not following along with all of this, that is to be expected. The idea of this notebook is really to see doing actual data analysis. You can, refer back to this. You have this notebook. You can play around with it, but it's kind of a taste of how we would actually do some data analysis. And Dask is a very powerful tool. It's also a pretty complicated one to use. So if you're doing a computation and it runs, usually if it runs in 30 seconds, that's very fast. I wouldn't think about doing Dask. If you run into very long or very memory intensive, where the kernel crashes because you've used up too much memory, then I would think about using Dask. So that's kind of my tips for using these. We're just gonna keep waiting for that to show up. I don't know why I have this extra line here. We can delete that. Are there any questions about any of this while we're waiting? Okay. Well, I hope that means that you're following along and not that I've lost all of you. So please let me know if you're confused. But we can see here that these numbers have changed. They don't say 0 anymore. So this is saying how many workers. There's a lot of vocabulary here in understanding the actual hardware of what we're running on. And to be honest, I still struggle to understand all the details. But basically, we have 2 threads per worker, which is why there's 10 and 5 here. And these threads are the actual, they're the ones that actually are doing the work that we want. So we'll actually compute our mean in this case. And you can see that we have 20 gigabytes of memory. So I believe that with 5 workers, that's 4 gigabytes per worker. That's just a default setting. There is another, instead of saying .scale, you can say something like, I actually forget what it is, but something like .memory, and you can scale the memory up if you need that. Okay, so if you print out client, this is also another view. This has the same link to the dashboard and has some information about the cluster. So it's another view that you can see what's going on. And if we go over here, you can see there's some blue things over on the side, which kind of means things are ready to go. So I'm actually going to make this a new window and put these side by side so that we can watch as this calculation goes. Okay, so we've just started our cluster. Now what I'm going to do is I'm going to run the same line of code that I did up above, where we did here, %time for mean SST.load, where mean SST was defined as such. So now instead of calling it mean SST, we're just going to run that line, because mean SST has already been loaded. So that would be really fast. So here we're just calling this line, we're calling .load, and we have a % time here. So we're going to see how long it takes. And once it starts running, you're going to see some action over here, which is telling you how your computation is being computed. So we can see immediately it starts with these tasks processing. So this is how much of the computation is being done. This over here on the left is how much memory is being used, how many bytes per worker. So we saw that remained very low. And this task stream, click here, if I hover over these, it actually tells you, as you see open data set, it's telling you what is happening at that time. So this was very quick, so it's now has finished. But you can see that most of these are opening a data set. So as we said, the main time bottleneck for this kind of calculation is actually the opening of data sets. But if I go over to this red one, for instance, it says transfer mean combine. So there it's actually doing taking the mean and combining this little chunk of data with other chunks of data. And let's see if we get a little green one here. Sometimes it's hard to, again, transfer mean combine, this one over here. Well, anyway, if you hover over, it kind of tells you what it's doing. And these colors are also indicative of what's going on. So I believe red is for when it's communicating between one another. But anyway, I'm getting into the weeds here. Anyway, this ran very fast. We can see it only took 12 seconds. That's, almost a third of the time that it took to run this one here. It was 34. So Dask just sped up our computation, which is pretty cool. Any questions about Dask or anything else that we've gone over? I know this is really a lot to throw at you, so hopefully you're soaking a little bit in, and as you work more in Python, you might come back to this and say, oh yeah, I remember that. No comments, no questions?
I mean, for
Mm-hmm.
the little of us, or the few of us that are just are new to such thing, it would seem
Mm-hmm.
to seem like magic or something. So that at
Yes,
least
yes.
we have an idea of what we're doing already. We have we have a glimpse of what you are trying to achieve, and so going back to the material you said was available last year, and also this, we can also try our hands on it after now. So I just feel we should just follow on and let's achieve this together so that after now we can
Yes, yep. Yes, thank you. I know it is a lot and it does look like magic. To be honest, it still feels like magic sometimes when I do it. But yes, this will be recorded. So if you, in a couple months, if you continue your Python learning, you can come back and say, oh yeah, she talked about Dask. What was that? And so a lot of this is maybe just so that you hear some of the words, some of the vocabulary, so it starts getting comfortable. And your data is probably going to be a bit different. Now, all of you have access to ECCO, so you can all start analyzing it right now if you'd like. But yeah, it takes time, like anything when you're learning. It takes time. You'd have to put in time to really grasp how it all works. So I appreciate that. And
say that again. We have access to ECCO now.
What's that? Do you have access to?
You said we have access to ECCO now.
Sorry, I couldn't hear what you were saying. Access to something.
Access to ECCO now.
ECCO, yeah. So you all have, I guess I should have mentioned at the beginning, hopefully you all have access to the Jupyter Hub, which is this where I am doing all of my calculation, in which case you can run this code yourself and load in the data right now. I can send a link to the Jupyter Hub, or you can go onto Slack, and I have a pinned post about how to access it. But
Okay.
I mentioned this yesterday as well, if you want to look at that. Let's see back here. The Pangeo data catalog. So Pangeo is a community for big data geoscience. So basically, if you do anything in the geosciences and you're interested in working with data and coding, the Pangeo community is really great. I'm going to talk about it a little bit more tomorrow. And it has this data catalog, and all of you have access to this Jupyter Hub through the school. And so you can access the Pangeo data catalog. So I'm just going through here, let's say browse the master catalog. And you can see here that we have atmosphere data sets, climate data sets, hydro, so hydrology data sets, and ocean ones. So I'm going to click on ocean. And if I scroll down, we can see that there's some altimetry, so some satellite products. There are a few models here. This is the LLC 420. That's they're just, I guess, more kind of model data sets. And then what we can see here is the one that we're using now, ECCO. But there are a lot of other different data sets. So you all can access this. If I click here, it will give me kind of information that we already saw of me loading in. This sometimes takes a little while, so we'll see, but it should give you the code. Here we go. So this says to load into Python, just copy and paste this. So all you need to do when you're on the hub, you do need access to this Jupyter Hub. You can just copy and paste. And if you note what's written here, it's the exact same thing that's at the top here. I literally copied and pasted that myself. And so that's how I knew how to access that, this data set. So you have access to it right now. And you can dig around, look at trends, do all of the analysis that you want. Is that helpful?
Yeah, thank you.
Any other questions or comments? Points of confusion? Okay, well, we are almost at time. I'll just talk through what is at the end here that you can run yourself. This is showing just kind of more intense computations and how you can do that. I won't go into those. You'll see some familiar things like group by, which we talked about at yesterday's tutorial. And here is where we actually, again, we actually load the data, and then we're going to plot it here. And this down here, these spatial derivatives, we're looking at a heat budget. And this is where these different grids come into play. So we have our I and J indexes, and that's for the temperature points. But for the U velocity and V velocity points, they're offset. So this is where, sorry, that was in my way. So this is where we have these staggered grids, like you can see here. So we have U points in green. We have C, so center points where temperature would be, in red. We have V, so that's meridional horizontal velocity, in pink. So these are all kind of offset. And this is called a C grid. And the reason why this is important to note is that when you're doing computations and taking derivatives, if you're used to taking derivatives at all, so this is for pretty, very mathematical analysis. If you're trying to take the derivative of momentum, for instance, then you're going to take this point minus this point, and you're going to end up with a derivative value for the center of the cell, which is on a different grid. So this does get a little bit confusing. But again, I guess this is just a little taste of what some of the challenges are with model data. But the good thing is we have tools like XGCM which it handles all of this for us. So that's what this big thing here is. We're saying use XGCM, and then we need to write all of this out just because we have these 13 faces. So a normal model XGCM can actually interpret this for us. But in this case, we have to specifically say, actually, there are 13 faces and we want them all stitched together. So this is, again, something where you can copy and paste and just use this. I did not write this myself. I copied and pasted it. So XGCM basically handles those staggered grids for us. And so when we do a derivative, it makes sure that everything ends up on the correct grid. So that's really what this was demonstrating. And you can, there are some nice little plots that you can make here at the bottom. So I will let you run those yourselves. And I will ask if there are any questions or comments or any other thoughts that you have that you might want to share or ask about. Okay, I hope that doesn't mean that everyone is lost.
Yeah, hello, Paige.
Yes, hello.
Yeah, I currently I have opened the Jupyter Hub on my PC, and I'm trying to locate the ECCO data. The ECCO data, I can't find it.
Okay. So did you open up a new notebook, or are you trying to find this notebook?
Yeah, I'm trying to find this notebook exactly. Yeah,
okay.
This particular one you're working on.
Okay, so I added this notebook last night, which means you need to make sure that you click on the link to the Jupyter Hub. Let's see, I have it. This is the PDF schedule. If you go to page 1, there's a link to Jupyter Hub. You want to, and you can see this long link. So make sure you click that, and it should sync everything correctly so that you can see this.
Okay.
If that didn't work, please do let me know, because it means that I made a mistake, which is very possible.
Yeah, let me just check that, and I'll get back to you.
Okay, because if you just say restart the hub or something like that, so the reason why we have this link, this is maybe interesting for you all to know, is that we have put all of our content on a GitHub site. If you're unfamiliar with GitHub, I'm talking about it tomorrow. And we put that here. So this is a public GitHub repository, which is what we call them. And this has all of the content that you can see on your Jupyter Hub. This is also just public. So you can see that it has ECCO data analysis here. You can click on it and it will load the notebook, and you can just view it. You can't run anything here, but you can view it online. Then you can download this. I'll go into more detail about how to do that. But all of this is accessible to anyone who wants it. Then the fancy thing that we have set up is this link, this big link that when you click this, that it comes up, is actually synchronizing your Jupyter Hub to this repository. And every time you click that link, it updates. So I just added this ECCO one last night. You can see it was added 15 hours ago. If you have not clicked that link since then, it won't be updated. So
yeah, I just did that, and I can see it. Thanks.
Oh, fantastic. Oh, good feedback. Thank you. Okay. So yeah, there are a lot of different things. And again, it might seem really overwhelming, and I really hope I haven't scared everyone away. So tomorrow I will talk a bit more. This was the most in-depth Python tutorial that we have. Tomorrow is going to be talking a bit more about Git and GitHub, which is nice to know about. You don't necessarily need to use it. If you're interested in doing more software development or software engineering, it is a very useful tool to have. So I'll talk a bit about that. And then I'll also talk about how and where to ask for help, because everyone struggles learning Python or learning any programming language, and knowing where to go to ask for help is really useful, and it's not always clear. So I'm gonna do my best, at least from my perspective, of how to best ask for help in these situations. Were there any other questions? Did others have any trouble accessing the hub? Something in the chat. Okay, great. Thank you. I think I was calling you Kunle because it's written there, but I think when you introduced yourself, did you say Moyo was your name? In any case, thank you for the feedback.
Thank you, thank you.
I do appreciate the feedback, and we will be sending out a survey at the end of this week, and there are a few questions about the Python content. And I hope you take the time to fill that out. It's really useful for me, and it will help you and others in the future. So, you know, positive and negative feedback are welcome, just so we can make sure we improve as needed. I hope you're all on Slack. I am posting the recordings. Actually, maybe I'll stop sharing at this point.